Every animal that ever lived solved the same problem. Something larger, faster, or hungrier was coming, and it needed an answer. Most answers look the same. Teeth, claws, size, speed, venom. The solutions that dominate the fossil record are the ones that make immediate intuitive sense. Move faster than what's chasing you, or fight back from the front. Offense and defense organized around the head, the limbs, the forward-facing architecture of a body built to either pursue or flee. And then there's a separate lineage of solutions. Quieter, stranger. Nature looked at the tail, the trailing, passive, structurally unremarkable end of an animal, and decided to put the weapon there instead. The evidence for what Stegosaurus's tail actually did isn't theoretical. It's sitting in a museum in Denver. A tail vertebra recovered from an Allosaurus specimen, the dominant large theropod of the late Jurassic Morrison Formation, contains a puncture wound. The shape of that wound matches a Stegosaurus tail spike, with limited room for alternative interpretation. The spike entered, the tail pulled back, and the bone preserved the record of that exchange across 150 million years. Stegosaurus stenops carried 4 of those spikes, arranged in 2 pairs at the tail's end. Each reached between 60 and 90 centimeters in length, roughly the distance from a human shoulder to fingertip. They weren't fused rigidly to the vertebrae. Fossil evidence indicates they were anchored in soft tissue, allowing a degree of mobility a rigid attachment wouldn't have permitted. The tail could swing laterally, and the spikes moved with it. The tail itself was built differently from the front half of the body. Its vertebrae show reduced interlocking compared to those further forward, increasing lateral range of motion. Combined with muscle attachment points along the caudal vertebrae, the mechanical picture is a structure optimized for horizontal swing, a lateral arc covering a significant threat zone at predator leg and lower body height. The name Thagomizer originated in a 1982 Gary Larson cartoon, before being adopted by paleontologists and eventually appearing in museum literature. It's the only piece of anatomical terminology in vertebrate paleontology that traces directly to a newspaper comic strip. The weapon itself is less strange than the name. A 150-kilogram tail assembly swinging at Allosaurus leg height and delivering 4 bone spikes into soft tissue was enough to make a predator calculate whether the meal was worth the risk. The vertebra in Denver suggests that at least once the calculation went wrong. Stegosaurus wasn't the largest animal in the Morrison Formation. It wasn't the fastest. But with the Thagomizer, the engagement became a cost-benefit question for the predator. That's what a successful defensive weapon looks like. Not invincibility, just enough uncertainty to make the attacker reconsider. Sauropods are not what comes to mind when the conversation turns to weapons. The image is fixed. Long neck, small head, vast body moving slowly through Jurassic vegetation. Passive. Enormous but unthreatening in the way animals without offensive equipment tend to appear. The assumption is so consistent that it rarely gets examined, which is why Shunosaurus keeps surprising people when it comes up. Shunosaurus, Middle Jurassic China, approximately 170 million years ago. A mid-sized sauropod by the standards of its family, around 11 meters long, relatively short-necked compared to later relatives, built like a browsing animal occupying the lower to mid-vegetation range. Nothing about the body plan signals what the tail was doing. The tail ended in a club, not a metaphorical description of a thickened tail tip, an actual bony club formed from fused vertebrae and enlarged osteoderms, with spikes projecting from it. The structure is unambiguous in the fossil record. Shunosaurus was an 11-meter sauropod carrying a spiked warhammer at the end of its tail, and it was doing this in the Middle Jurassic, earlier than Stegosaurus, earlier than ankylosaurs, earlier than almost every other tail weapon system in the dinosaur record. That chronology matters. The standard narrative of dinosaur tail weaponry usually centers on ankylosaurs as the apex expression of the concept, the animals that perfected it. Shunosaurus disrupts that narrative not by being more sophisticated, but by being first. A sauropod, a group usually categorized as defensively passive, arrived at the spiked tail club before the specialized defensive lineages had fully developed. The predators Shunosaurus faced included large synraptorid theropods in the 7 to 9 meter range. Against animals that size, a Shunosaurus capable of delivering a spiked club strike to the skull or ribcage was a far more difficult target than one that couldn't. The tail reached far enough, and the club was heavy enough that a clean strike represented genuine injury risk for the attacker. It never entered popular consciousness the way Stegosaurus or Ankylosaurus did. The fossil material came out of China in the 1970s, and the genus never quite crossed into mainstream prehistoric iconography. That's a cataloging problem, not a biological one. The weapon was real. The sauropod built it first. Not every tail weapon was built to make contact. Diplodocus longus, late Jurassic North America, Morrison Formation, roughly 154 to 152 million years ago. One of the longest dinosaurs in the fossil record. Total length estimates reach 26 meters in larger specimens, with the tail accounting for roughly half of that. The tail tapered progressively from a wide, heavily muscled base through dozens of vertebrae that became increasingly small and lightweight toward the tip. The final section, sometimes called the whiplash, narrowed to vertebrae only a few centimeters across. In 1997, a biomechanical study modeled the wave propagation dynamics of a Diplodocus tail under muscular actuation. The physics followed the same principle as a bullwhip. Energy transferred from a heavy base through progressively lighter segments accelerates as mass decreases, concentrating velocity at the tip. The study concluded that the tail tip could reach speeds exceeding the speed of sound, roughly 1,200 kilometers per hour at the terminal vertebrae. The crack of a whip is a small sonic boom. The tip breaks the sound barrier and the pressure wave registers as sound. A Diplodocus tail doing the same thing at full actuation would have produced an audible report across a significant distance. What that was used for is where interpretation becomes contested. The contact weapon hypothesis, that Diplodocus used the tail to strike predators, runs into a structural problem. The terminal vertebrae are fragile, thin-walled, and optimized for speed rather than impact resistance. A hard strike against a solid target would risk fracturing the very tip that generated the velocity. Several Diplodocus specimens show healed damage in the tail vertebrae, consistent with this kind of stress. The alternative interpretation is acoustic, that the crack itself was the point. A display signal, communication device, or deterrent working through sound rather than physical contact. A supersonic crack at close range is disorienting in a way that's difficult to quantify, but easy to imagine. Both interpretations may be correct. A tail capable of supersonic velocity could function as a contact weapon against softer targets while serving as an acoustic signal in other contexts. What the tail was not was passive. 26 meters of animal, half of it a tapered structure capable of generating a sonic boom on demand. The back end of Diplodocus was doing something. The exact something remains the most interesting open question in its biology. At some point during the late Jurassic, A mid-sized stegosaur in what is now Sichuan province developed a solution common among species facing high survival pressure. It didn't stop at one weapon system. Gigant Spinosaurus siquanensis, roughly 4 to 4.5 meters long, placing it on the smaller end of the stegosaur size range. The backplates were reduced compared to Stegosaurus, less dramatic, less visually dominant. What drew attention instead were the shoulder spines, paired structures projecting laterally and slightly upward from the shoulders, enormous relative to body size and extending well beyond the animal's lateral profile. The tail carried spikes as well. A standard stegosaur thagomizer, the same lateral swing weapon seen in Chapter 1, scaled to a smaller but still functional frame. Which raises the question, were both systems doing the same job? The shoulder spines present an interpretation problem that hasn't fully resolved. Their angle and position make them awkward as active offensive weapons. Gigant Spinosaurus couldn't easily drive them into a predator the way horned animals charge. What they could do was widen the animal's apparent profile, making a 4.5-meter stegosaur appear larger and more dangerous from the front. A predator approaching head-on encountered the display before it reached the animal. The tail spikes handled the rear approach. The shoulder spines handled the frontal presentation. Two systems, two threat vectors, one animal. Some have argued this represents over-engineering, that maintaining two weapon systems would be metabolically inefficient. But the anatomy doesn't clearly support that. The shoulder spines required relatively minor skeletal modification beyond the scapular support already present. From a biological standpoint, they were a low-cost addition to an already armed frame. The fossil record for Gigant Spinosaurus is limited, and details of the shoulder spine orientation still involve some reconstruction. What is clear is the ecological setting. Late Jurassic Sichuan hosted large theropods such as Yangchanosaurus and Sinraptor, predators 7 to 11 meters long capable of targeting a 4.5-meter stegosaur. Against that predator guild, covering multiple attack angles with different weapons was not an unreasonable strategy. It wasn't elegant. The species name translates directly, Crurivastata, destroyer of shins. When paleontologists named it in 2017, they weren't being dramatic. They were being precise. Zool crurivastator, late Cretaceous Montana, about 75 million years ago. An ankylosaurid, the club-tailed lineage of armored dinosaurs, recovered from the Judith River Formation in an exceptional state of preservation. The specimen retained not only the skeletal structure of the tail club, but articulated osteoderms and sections of soft tissue impressions. The external surface of the club preserved the texture of the keratin covering that once overlaid the bone. That matters because most tail club reconstructions rely on bone alone. Bone shows the core structure, fused vertebrae, and enlarged osteoderms forming the striking mass, but not the full geometry of the weapon in life. Soft tissue adds mass, alters the surface profile, and affects how force spreads on impact. The Zool specimen allowed researchers to examine the complete weapon rather than just its internal framework. The club itself was broad and oval, positioned at the end of a tail stiffened by interlocking bony tendons. That stiffening is what made the weapon functional. A flexible tail would dissipate energy before it reached the club. A rigid tail transfers the momentum of the entire swing into the terminal mass. Biomechanical modeling of ankylosaurid tail clubs suggests the impact force was sufficient to fracture the lower leg bones of large theropods. Not bruise, fracture. A predator with a broken tibia or fibula was no longer a functional hunter. The name reflects the mechanics. A lateral swing from a grounded ankylosaur naturally intersects a predator's lower legs. Shin height was simply the most likely place the weapon would land. Zool also carried skull horns and large spikes flanking the base of the tail, layered deterrents that made approaching the club increasingly costly. The specimen is housed at the Royal Ontario Museum and remains one of the most complete ankylosaurids ever recovered. Everything about Seychenia was built for a world trying to kill it before any predator arrived. The Gobi Desert, late Cretaceous, about 80 million years ago. Not a desert in the modern sense. The paleo environment was arid and seasonal rather than the vast sand system it would become. But dry, resource scarce, and climatically volatile enough that animals there were shaped by environmental pressure before ecological pressure even entered the equation. Seychenia chulsinensis was built for that context first. The armor and tail club came second. The osteoderms covering Seychenia were among the most extensively developed in any ankylosaur, thick, tightly arranged, protecting not just the back, but extending along the sides, minimizing exposed soft tissue. The palate was reinforced, suggesting adaptation to dusty, abrasive vegetation, typical of arid environments. Even the nasal passages showed structural complexity, possibly linked to humidifying dry air before it reached the lungs. The tail club was robust and proportionally heavy, mounted at the end of a stiffened tail, reinforced with interlocking tendons. The predators Seychenia faced in the Gobi included Tarbosaurus, the Asian counterpart of Tyrannosaurus, slightly lighter, but operating on the same predatory logic. Against Tarbosaurus, the tactical situation was specific. The predator attacked with its jaws, meaning it had to bring its head close to the prey. A tail club that naturally swept through shin and lower leg height forced the predator into a proximity problem. Getting close enough to bite meant entering the club's strike arc. Meanwhile, the armor made flanking attacks costly and uncertain. And then comes the one that needs no introduction, Ankylosaurus magniventris. Its tail club wasn't the first of its kind, nor the earliest discovered or the most unusually preserved. What it was, and remains, is the most mechanically complete expression of the tail weapon system dinosaurs ever produced. Late Cretaceous North America, roughly 68 to 66 million years ago. Ankylosaurus lived at the very end of the age of dinosaurs alongside Tyrannosaurus rex and Triceratops in the Hell Creek Formation. An ecosystem so crowded with famous species that Ankylosaurus is sometimes overlooked simply because of the company it keeps. The animal measured roughly 6 to 8 meters long and weighed between 4,800 and 8,000 kilograms. Its body sat low and wide to the ground, wrapped in dense armor. These osteoderms weren't decorative plates, they were structural protection, thick enough and tightly arranged enough that penetrating them required force even Tyrannosaurus struggled to deliver from most angles. At the rear sat the defining feature, a fused tail club. Osteoderms at the tail's end had merged into a single rigid mass, attached to a tail stiffened with ossified tendons. That stiffness mattered. A flexible tail would bleed energy through movement, but this structure transferred the full momentum of the swing directly into the club. Biomechanical modeling published in 2009 by Victoria Arbour estimated the impact force between 2,165 and 4,059 newtons, enough to fracture the lower leg bones of large theropods. Which brings us to the animal this weapon was effectively calibrated against, Tyrannosaurus. Both species shared the same landscape in Hell Creek. A Tyrannosaurus approaching Ankylosaurus was approaching an animal capable of delivering several thousand newtons of force directly to its shin with a lateral swing it might not have time to avoid. Tyrannosaurus did have one advantage: height. Attacking from above and targeting gaps between armor plates reduced the exposure of its legs. Whether that advantage consistently worked is unclear. The fossil record preserves Ankylosaurus specimens showing signs of predator attack, but none showing evidence the attack succeeded at the site of engagement. That absence isn't proof, but it is data. Ankylosaurus lived right up to the end Cretaceous extinction. The tail weapon lineage that began with early spiked clubs in the Jurassic reached its final and most refined form here, just before the asteroid ended the ecosystem that had required it. 66 million years of tail weapons ended in the same geological moment as everything else. The weapon outlasted almost everything it ever faced, just not that. Every animal in this documentary made the same choice. Build something at the tail end, refine it, use it. Nodosaurids didn't. That requires context, because nodosaurids were not undefended animals. They were heavily armored, osteoderms covering the back and spikes projecting from the neck and shoulders in some species. Their entire body plan was built around passive protection. One of the best examples is Borealopelta markmicheli, recovered from the Cretaceous of Alberta in 2011. Its exceptional preservation revealed not only armor arrangement, but even original coloration, reddish-brown on top, lighter underneath, counter-shading, camouflage on a multi-ton armored animal. That alone tells you something about the predator pressure they lived under. The tail, however, remained unarmed. No club, no terminal spikes, no structural modifications like those seen in ankylosaurids. The biological split happened early. Ankylosaurids developed the tail club, while nodosaurids diverged before that innovation appeared and never independently developed it. Which raises the central question. Both groups face the same predators, large theropods built for active pursuit. Both invested heavily in armor. One lineage built an active weapon, the other did not. The nodosaurid strategy was straightforward. Low center of gravity, wide body, armor covering the surfaces most accessible to attack. Lateral spikes along the shoulders and neck made flank approaches costly. A predator, unable to penetrate the armor from above, had limited options: attempt to flip the animal or move on. The defense required almost no action from the animal itself. Stay low, stay armored, remain structurally difficult to kill. The ankylosaurids chose a different path. They combined armor with an active weapon, a stiffened tail capable of delivering powerful strikes. That required muscle investment, positioning, and timing. Both strategies worked. Nodosaurids and ankylosaurids coexisted across much of the Cretaceous, under the same predator pressure, and both lineages survived until the end Cretaceous extinction. One built the most sophisticated tail weapons dinosaurs ever produced. The other never built one at all, and both endured for tens of millions of years. Nature doesn't optimize toward a single answer when multiple answers work. It fills the available solutions and lets the environment sort the rest. What ended both of them wasn't a predator that found a gap in the armor or a theropod fast enough to avoid the club. It was an asteroid. 66 million years ago, the selection pressure that had shaped every weapon and every armor plate and every counter-shading pattern across the entire Mesozoic stopped applying simultaneously. The nodosaurids never needed a tail weapon. The environment they lived in never required them to build one. That environment just happened to end.